Hello, everyone. Good afternoon. Welcome to the OC seminar. It's a very special occasion in which we are welcoming Professor Mateja Jamnik from the University of Cambridge, the Computer Science Department.
Can you record that?
It is already being recorded. So it is an honor and a pleasure to have you here, Mateja. And we will hear her talking to us today about how can we make trustworthy AI. Thank you so much.
Yeah, thank you very much, Giselle. Thank you, Marco. Thank you, everybody, for inviting me to all the way from Europe to come here to talk to you. And I'm going to tell you a little bit more about my work. We had a bit of a conversation yesterday already. So feel free to interrupt whenever you want. We have a very long time slot, so I prepared to talk for about 45 minutes.
Forget. Nobody was successful in this seminar. Never happened.
Yeah, so I'm very happy for you to ask questions as I go along or save them for later, whichever you prefer. I don't mind at all, so it's nice to have a conversation. But I'm going to tell you more about my work today. So, and I entitled it "How Can We Make Trustworthy AI?" And that was quite deliberate that I put a word "make" in there, because this is what I do. I build systems and I create AI machines. Of course, everything that I'm going to say today, if this is going to react, yeah. So everything that I'm going to say today is not just my work, like mine individually. It's work of me and my team, which is lots of PhD students, lots of postdocs, and lots of collaborators. And these collaborators are, you will notice that the work is inherently interdisciplinary. So you will see here collaborators that are computer scientists, collaborators that are philosophers, collaborators that are mathematicians, educationalists, and so on. So I'm very thankful to everybody. So when I say we, I mean the team, everybody. I'm very intimately involved, obviously, but and I only put the people here that are directly involved with the topics that I'm going to cover today. But obviously, my work's influenced with work and collaborations in other projects too. So there's not enough space to. So let me start with the fact that, like, a few years ago, when I was always asked about to talk about disrupting power of AI, and the main concern was always, fear of AI. But and the questions that I was being asked, even for national radio stations and so on, is, are robots going to take over the world? And the media was full of articles like these of Blade Runner and Ex Machina. And these robots were portrayed as populating our future and being indistinguishable from, in their behavior, from human beings.
So can we be sure that you are not a robot?
Yeah, pinch me. Or ask me a very difficult question. But I think that, so these robots were portrayed as indistinguishable in their behavior from human beings. But today, I think that we have moved on, actually. And of course, those questions haven't gone away, whether AI is going to destroy us and whether we should fear AI. Those kinds of questions didn't disappear, so we can still see them in the media. But the world has changed, I think. So, and despite the fear, we're actually embracing AI, and now we are using it in our daily lives. And AI is essentially now ubiquitous today. We have cars actually driving without human drivers, robots on the streets of my hometown in Cambridge in the UK that are delivering our groceries, like the one in this
There are
clip.
many near my home in Irvine, because I use it in UCI campus to transport books from one department to other. So when I stay home, often there is one that goes in front of me.
Yeah.
But
so
here we do not use it.
watch this. This is going to stop to avoid the lady. So we have them to deliver groceries. We have call centers that are conversing with us, and we use AI to make decisions even in criminal court. So what are the challenges that people, or the questions that people are asking about today? And what are your questions that about AI today? So today I get asked questions like, what are the risks of AI? Should I trust these intelligent machines? Do I understand the solution or the prediction that the AI machine is recommending me? Or is it even aware of me and my needs? And is it taking into consideration all that we as humans have discovered? So, or is it just crunching patterns in an intelligent kind of way, for sure? But it's finding the most common denominator to all of the people that it has data about, which, by the way, it might not even include me. So, as a professor of AI in Cambridge and as an AI system builder, I'd like to bring a practical perspective on how we can tackle these kinds of important challenges of AI and how we can make AI machines trustworthy. So, in this talk, I will emphasize 4 aspects of AI that demand our attention, in my opinion, and in particular, I select those because they highlight my particular interest in finding technical solutions too. And these are, first, is intuitiveness. So the system needs to be able to think in more human-like ways. They need to produce solutions that are sort of intuitive to us as humans, and that they provide us with some sort of insight, like eureka moments.
So you mean that it has to simulate intuition, or that it needs to have intuition?
I will show you, and I hope it will become clearer, but if it's not, you can ask me. So 2, adaptability. They need to be able to interact with us in human-oriented ways, not machine-oriented ways. So rather than us adapting to them, they need to be able to adapt to us. 3, explainability. So they need to be able to explain how they arrived at the solution that they're presenting us, or a prediction or a recommendation. So they need to explain to us, or it needs to be clear to us how the prediction was made. And 4, they need to include human knowledge. So rather than just using data to spot patterns, they need to be able to capitalize on the wealth of domain knowledge that we as humans have developed or discovered over millennia, and that is today digitized in formal repositories like ontologies, or informal ones like Wikipedia. Of course, there are other important aspects of AI that are pressing too, and like, for example, privacy, like regulation, like ethics. But I will not cover those aspects and challenges and types of challenges today, particularly because they are not the center. I'm not an expert in them, and I leave that to ethicists and lawyers to make progress in. I'm here as an AI builder, and I bring technical solutions to these 4 aspects that you see here, and I'm going to say more about them. And I think that by addressing these all of these aspects, we build better AI. So, and this contributes to making AI machines more trustworthy, and while we are also mitigating the potential risks. So, in this talk, I will introduce technical innovations that will focus on the intuition and adaptability of AI, the explainability of their output, and the incorporation of human domain knowledge. And I'm inviting you to join me whilst we are exploring these practical solutions that will lay some of the groundwork for an AI future built on trust. Yes.
Okay, really exciting intro. I'm really excited to see where this goes. Usually when people talk about these challenges, they use the word alignment. Do you see trustworthiness as a synonym for alignment? How are those the same or different concepts?
So I'm not making statements about trustworthiness. I'm making statements about the solutions, technical solutions that contribute to, so I'm not like a researcher in trustworthiness, right? I'm a researcher in AI building systems that are more explainable, adaptable, intuitive, and incorporate our knowledge. And all of those, I think, contribute to these systems being better and contributing to us being able to trust them more. Alignment, it's a technical term, actually. So, and it will, to do something with different types of data, whether they align and whether you can explore the interactions between different modalities. I think that's what you're referring to.
I was thinking more like the principal agent problem. We would call it in economics. How do you manage it and get it to do what you want to do? Maybe that is or isn't what you're saying.
Okay. Well, come back to me if I don't answer that through the talk.
Awesome.
Right. So I'm going to now take you a few years back. So when I was a child, I really, really loved maths. So what fascinated me most was the beauty and the elegance of the solutions that I saw, but also that sometimes I was even able to come up by myself. But I was also really interested in people, so I was wondering, how do people come up with these elegant and beautiful and intuitive answers to these problems? And then as I was going through my education journey and work journey, I started to investigate this human thinking and trying to make machines do the same. And so I want computers to come up with solutions that are intuitive to humans. So the overarching, I think, theme here is that I'm advancing human-like computing, AI, if you like. So here's an example of what I mean by intuitive human reasoning. So take a look at this parallelogram and what is its area? How would you go about computing it? So if you're an expert, then perhaps you might use an integral. A bit of an overkill, I would say, but there you go. If you're a child, a primary school child, then perhaps you are going to tile it with these kinds of unit squares. But for the rest of us, well, perhaps...
You are the rest of us.
Well, I couldn't use somebody else. I had to put the rest of us. Not the expert, not the genius, not the child.
Last year I had a default, I was modest. This year I am perfect.
Okay, so perhaps we would then use a diagram like this. So of course the second solution that I showed you is not accurate, but it's at least an approximation that eventually, as one becomes an expert, could lead to understanding the integral solution. And this solution is a visual one, and it gives us the intuition that of the area of the parallelogram. So it's clear here that the area is the product of the width and the height of the parallelogram. But you might wonder how, well, I was wondering, how would we go about building machines that are going to come up with solutions like this? And so in my work, I'm looking at how humans are solving mathematical problems in intuitive ways. And then, well, when I say intuitive, so if I give this talk to cognitive scientists, they will also, jump up and down and not like the word intuition, right? So for them, I usually say insightful, so that it gives us some kind of understanding and insight into why the solution is correct. So yeah, so I was interested in investigating this kind of human reasoning, and then with these types of eureka moments, and particularly using diagrams. And then I built AI systems that do this in the same kind of way. So let me give you another example. How would you go about proving this algebraic identity? So this is a theorem that many of you probably remember from school. And now my kids are learning about it at school. And the task is to show that adding the first n natural numbers can be calculated by using this formula, n times n plus 1 divided by 2. So, well, this is how state-of-the-art theorem prover Isabel does it. All clear? Lots of symbols, lots of numbers, lots of rules. And the solution actually relies on mathematical induction. So it's quite a bit of expert knowledge. You might wonder how ChatGPT would do it. And here is how. Actually, this pretty much follows the Isabel's proof. You need to understand mathematical induction and rely on it for the general case of all natural numbers. And then ChatGPT comes up with a similar in spirit proof that the Isabel does.
Not very intelligent, the ChatGPT.
But let me show you how I was taught this in school. We used a diagram. So first, natural numbers are positive whole numbers. So let's represent them using these counters. And so let's draw a rectangle, which is n counters wide and n plus 1 counters high. And you can see in my picture that I've used n to be 5, I think, yes, 5. So my rectangle is 5 counters wide and 6 counters tall. And this now represents my n times n plus 1. Now, let me split this rectangle kind of down the diagonal. And you can see that what we get is 2 identical triangles, and each is n counters tall. So in my picture, both triangles are 5 counters tall. Okay, so now let's just take one of these triangles, so half of n times n plus 1, so that's why we have now n times n plus 1 divided by 2, so I get now one side of my equation. Okay, so we've got just one of these triangles. So if we now start splitting aside from this triangle and continue doing this, you will see that we are getting a succession of increasing natural numbers. Okay, and so our triangle basically shows that 1 plus 2 plus 3 plus 4 plus 5 equals to 5 times 5 plus 1 divided by 2. So, but notice how I showed you a concrete example here for n equals to 5, and we were able to prove the theorem. But we can also see, not just for that particular case, but we can see that whatever number I take, 53, 99, 1001, the proof will still be the same, and it will be true.
How do I see it?
Yeah, how do you see it? You see the pattern, right? You see that we're not violating, when we increase the number, we're not violating the steps that we are taking. So the steps will stay the same. It's a procedure. And so we can see that this procedure is correct. So I want to capture this kind of intuition on machines. So I designed and implemented.
I'm wondering whether sorry? Okay. I'm wondering whether what makes us sure that this is the same for any number is not some sort of inductive process. We add a new column and a new row, and so in some sense we begin with the first 4, and Okay, we continue this way to the end,
Yeah.
and then we add another, and we discover that the pattern does not change when they
Yeah,
go from
exactly.
one
You
to
can
the
see
other.
here even 1, 2, 3, 4, 5, right?
Yes, but this is not the same that to say that they can repeat the same pattern for any number n, is that when you pass from n to n by 1, the pattern does not change. And so in some sense, you intuitively apply induction.
Yeah, yes. In fact, that is true, but it's something more than just induction, right? And I will say something more about that in a second. So I designed and implemented a system where you could solve problems by using these diagrams in precisely this kind of way. Spatial manipulations are now the inference steps of the solution. So first, in this system, you need to construct a couple of examples. So let's say for the case of n equals to 5 or n equals to 99. Then I built an algorithm that extracts this pattern in this procedure in a program that we call a schematic proof. Notice that the generality now is captured in the number of inference steps in this recursive program. So, for example, in this case, my procedure would be something like this. Now, I used formal methods in order to justify this step of why we can use a concrete case of a diagram, in my case, n equals to 5, and a concrete solution to capture the general solution for any number. So in particular, I refer to, or I rely on what's known as the constructive omega rule, which is a logical rule that allows us to make this conclusion. And it says it's stronger than induction because it says that if you can capture this pattern in an effective procedure, effective in a formal sense, so like, for example, in a recursive program, then you can conclude the general statement. So constructive omega rule has been used not just, I was not the first one to use it, I was the first one to use it to justify this step in the visual, in the diagrammatic world, but it's been used in arithmetic and in other domains to capture the generality of the statement as a replacement, or not, it's actually stronger than induction. And it turns out that, that it actually enables you to often avoid the need for generalization, which is a very hard problem, especially if you're trying to automate.
How you formalize the omega rule in the program?
The constructive omega rule, because the omega rule is an infinite rule because it asks you to prove infinite. Constructive omega rule says if you can find an effective procedure. So if I find a recursive program that produces an output for each input, then I can rely on this. Obviously, I have to prove that the program is correct. But yes, but so I can make that inference.
If you put one, it gives you 1, it goes to 2,
it gives me a proof for 2. Yeah, if I give it 99, it'll give me a proof for 99. Yes, it's a program.
And the proof of the correctness of the program would involve induction again.
Yes.
Yeah.
In fact, yes.
Mm-hmm.
In fact, I will say that next. So, so basically, finally, if the solution is found, then the system will guarantee that it's a correct solution, and it will do this through meta theory. So we will reason about the correctness of the proof, so the program, no longer about the theorem. Yes. So let me just say this. So this approach of so yeah, you can see this in the last step. We want to use. I often refer here to but we discussed this yesterday. I will refer back to the fact that mathematicians would stop in the second step, but logicians and computer scientists need to verify everything. So we need to show that the verification happens. So we do this in the meta theory here. But this approach of using schematic proofs is general and can be used to prove many theorems and examples of many different domains, visual or symbolic. So
Yes, but my question is, now you have a program that for any n given,
Yes.
but this program is proper to this particular problem or in general. So you have an implementation of the omega rule, or you have an implementation of the application of omega rule to this particular case.
No, we have the implementation of the program, and we use omega rule as a justification that this is the general statement. So we did not implement. I guess by proxy, this is the schematic proof is the implementation of a constructive omega rule, because it's producing a recursive program, basically, the way it's implemented in this case. But there are other effective procedures, but not necessarily recursive, but the recursive are the most common, I guess. So
It's interesting you mentioned that Logicians stop in the second line.
Yeah.
Perhaps because they are happy with generalization
Yeah.
over free variables, right?
yes,
They don't have to construct it.
yeah, I mean, the proof is done by them,
Yeah.
right?
Stop there because generalize.
And if
over
they
variables.
trust it and believe it, then there's no need to verify, but we want to verify it.
You need it.
We want to have a guarantee that it's correct, especially if we're deploying these kinds of subsystems in real life. Like, for example, in hardware, right? Doing this a lot, so, right? Okay, so I showed that we can make computers solve problems in the same kind of way that, humans do it. But I was also wondering if machines could discover new, unseen intuitive solutions to problems that people have not been able to solve or understand for a long time. And to tackle this, we're currently using AI techniques like machine learning, and I'm going to return to that a little bit later. Okay, so my first take-home message here is that we can make AI machines produce more insightful and human-like solutions. They can think in more human-like ways, and such machines are then enabling us to understand their output better and therefore trust them more. So this brings me back to my love of maths and people and trying to make machines more human-like. And so I got increasingly frustrated because I had to work with machines that in a way that was dictated by machines. And I was wondering, so why can't my sat-nav understand that I've been living in Cambridge in the UK for ages, and that it's far more helpful to tell me to turn left at the round church and then right just after the grocery shop in town, rather than say, turn left in 250 meters, go straight for 50 meters, then turn right in 200 meters.
The map of Cambridge?
No.
Does not seem so.
Abstract design. And so I started to look into this, of what kind of representations people use and what machines use. And can we build machines that can have some understanding of the human user and the problem that the human user is trying to solve? So how can a machine decide what is the most appropriate way to interact with the user, their background, and their level of expertise, and adapt to them accordingly? So remember the parallelogram that I showed you earlier, and how Newton might choose to use integrals to a child might use squares, and the rest of us might use rectangles and triangles to compute the area of parallelogram, or in fact even the complex Isabel's proof of the theorem about the sum of all natural numbers and the human intuitive visual solution that we just saw. I think that for people to trust AI, these intelligent machines need to be able to interact with us in more human-like ways. I think they need to represent problems and solutions in ways that are adapted to us. And this is basically my second aspect of AI that I want to talk about, and I want to address it now. So let me give you an example of what I mean about the representing problems and adaptability of machines. So here's an example of a problem that we want to solve. It's been probably on many people's minds given the pandemic that we went through recently. And the problem basically says that 4% of the population has some disease, and of those that have the disease and they take a test, the test is accurate 95% of the time. And those that don't have the disease, the test is accurate 90% of the time. And that if you take the test and it comes out positive, what is the probability that you have the disease? Okay. So
Why the text is expensive is relevant in the solution?
yeah, it is not relevant, but it's a red herring that I put there deliberately because we are now trying to model this and we have to decide what's relevant and what's not relevant to the problem. So typically, this is probably what you would find that the system will try to, how the system will try to represent this problem. So we will be using PR to encode probability, and then we will be using things like conditional, like typical Bayesian conditional probability. And so then the test will be, here are some things about the accuracy of the test. And then the question is, what's the probability of D, so having the disease, given T, so that you have taken the test and came out positive by the test. Okay. And then, so this is, I refer to this as Bayesian
Bayes' theorem
symbolic.
should be make as able to calculate it.
Pardon?
Bayes' theorem should make as able to
Yes,
make it.
yes. So, indeed, I hope that you all remember all of your probability stuff. Don't worry, you don't need to remember all the details from your undergraduate classes or perhaps even high school. And then the system would apply these rules, and these axiomatic rules, to derive a solution in this kind of way. Okay? So this is my base solution. Don't worry, you don't need to understand the detail. You'll see the list in a minute. But let me show you another way. So I'm going to use areas and a visual representation.
The result is not very nice, only 0.28.
Yeah, it's surprising, right?
It's very bad.
Very surprising.
Very bad.
That's
Exactly.
well known, kind of.
So, yeah.
It's very, because the disease is very rare.
Okay. So shall we see why? You might see it. Okay, so I'm going to show you a visual representation rather than the Bayesian symbolic representations. And so here I will have a square of size 1 that will denote the entire population. And now I have a section of that square, so you can see this 4% that denotes that these are the people that have the disease. So not many, right? And now of those 4%, 95% of those that have the disease, the test T will identify correctly. And so this is the blue and lined area here, right? So, and the remaining square, so 96% of the population does not have the disease. But we know that for those that take a test, it's 90% accurate. So 10% of those will come up as positive, even though they don't have the disease. And so this is the blue area at the top there across. Okay, so this is also known as the false positive area. Okay, so all of the blue area are those testing positive, whether they have a disease or not. And the answer to the problem is basically the proportion of all those that have the disease and test positive with all of those that just test positive. So it will be the ratio between the lined and all of the blue, right? And so it is. So this is how we can calculate here the percentage. Okay, so let me do a little poll here by show of hands. So
But I'm wondering whether the geometric representation is not in fact a representation of the bias theory.
It is.
It is.
So it is the same calculation.
Yeah,
It is.
It is.
It is,
Yeah,
it's
of
just
course
a
it
different
is.
representation, right? So my question here is, who understands and prefers this last one, say the visual area solution?
It's a conjunction of the two.
You can abstain if you like, or put your hand up for both if you like.
I prefer, but
Right,
not
hands up, those who like prefer the visual.
Yeah, the visual is much better, easier to explain, of course.
Okay, so I would say probably 70%, probably even more, 80%.
You prefer the area solution?
So who prefers the Bayesian symbolic solution? Okay, so we have about, what, 20% of people, maybe, roughly.
But I can qualify my answer. I prefer the Bayesian one, but I understand better the other one.
That's completely fine. That's completely fine. And in fact, when I give this talk to logicians, they will all prefer well, not all, but the majority will prefer the Bayesian solution because they trust it more.
I
Because
think
they see
that,
it written as equations and they trust the
So,
process.
Jose, is your attitude the following? You look at the area solution, you understand it, but you are not completely sure that it's right. So you use the Bayesian solution to guarantee that is in fact your intuition of the area is the correct one. This is
But they're the same solution. It's exactly the same solution.
Yes,
People
but
don't
you do
trust
not
that,
see in the same
right?
way. You do not see in the same way. No, you do not. The solution is the same. But I was the first one to tell it, but the representation is different.
Okay, yes, yes,
Have you asked other groups of scientists,
yes.
like physicists?
I've,
Do they give you a different answer than what you said logicians or mathematicians?
yeah, I was in the formal community and formal reasoning. And they were all logicians, mostly mathematicians. They all preferred, well, logicians. They all preferred the majority preferred the Bayesian solution. And overall, for different audiences, the majority usually prefers or understands better the visual solution.
So maybe the most germane question is, what do the epidemiologists do?
What do you teach
It
doctors?
doesn't really matter. I want the system to be able to gauge that and decide correctly for that person, right? So that's my point here. You had a question there.
Yeah, I was just wondering whether maybe I would prefer the Bayesian one or the geometric one, because the fact that their area seems to be like kind of not germane to the problem, right? So maybe it's more intuitive when I look at it, but it introduces kind of notions that are not relevant.
Maybe. I would disagree, but but yeah, for some
What's the
people.
point?
That area is not relevant to the problem.
Yeah. So right. So kind of
You don't like
there's a
the fact
reason
that
to
it's
prefer a
spatial
solution
thing.
that only
Yeah.
uses notions that are relevant to the problem.
You know, I think
You
the.
don't have to do it like
How can, I ask myself, can I
one criteria.
forever using areas, or I have to rely back when I have harder problems to the numerical solution?
Yeah,
That's
no,
why I
in
mean,
fact, you're
I
completely
don't believe
right.
that the area will be solve all problems.
No, it won't.
Yeah,
In
so
fact,
it
if
is
you
right.
have three conditional probabilities or three variables,
Yeah.
you can't represent it in a 2D
Then you can, so you're lost.
space, and you lose the intuition. Absolutely. So, and this is exactly my point here. So, these two are not the only representations that I could have used. You will see that there's also contingency tables or probability trees, and you might prefer one of those, or you might be more familiar with one of those. So why would we use different representations? Well, evidently, just from this room, there is a disagreement of what people prefer. That not everybody thinks the same. So. So yeah, roughly, what did we have? 30% roughly, let's say. And so my point here is that different representations make different things evident. They require different kinds of knowledge, and they allow us to make different kinds of manipulations. And this is my point here. Like, people think and use these tools differently. So I want AI machines to be able to gauge that, and so that they will represent a problem and its solution in a way that is adapted to me, right? To the human user who is trying to solve a problem. And so typically these machines they usually have only one fixed type of representation, and usually it's symbolic in some kind of logic or something like that. When they interact with us. So for example, with the sat nav, it will be in terms of 250 meters left to 300 meters right, and so on. Or the symbolic Bayesian solution that I showed you earlier, or even Isabel's logical proof of the sum of all natural numbers that I showed earlier. So I was wondering, how can we go about analyzing potential candidate representations and also user preferences and levels of expertise, so that we would be able to give AI systems this ability to adapt to us? And well, this was and is still, or was, an open research question. We don't even have a language to talk about representations and analyze them and talk about different properties of representations, regardless of whether they're formal, like logics, or informal, like diagrams. Yes.
Don't we kind of have this already, though? You can write more and more complex prompts for like ChatGPT. So couldn't I just say, like, give me some sort of visual solution to this problem rather than a Bayesian solution, right? It might give you the first one initially, but then you can fiddle with it a little bit and get the different representation that's more suited to you. So do we not already have some kind of adaptability?
You have to prompt it, first of all, and second of all, it needs to know about that kind of representation, and third of all, it needs to know about you, and ChatGPT doesn't.
Okay, so the idea is to kind of circumvent this and have a nice...
Yes, so you have an analysis of both the... in fact, I'm going to say it in a minute here. So, so we have in our we call it rep to rep because it's representation to another representation project. We developed this framework within which we can analyze representations with respect to the problem at hand and the user who's trying to solve it. And the framework consists basically of a formal language and algorithms that basically answer two questions. What kind of concepts can the representation convey, encode first of all, and then convey? And we call it informational suitability of the representation. So can I talk about all the concepts that I need to talk about in order to solve the problem? And two, what cognitive burden does the representation place on the user? So it needs to gauge what level of expertise the user has, and whether it would be one representation would be more suitable than another. And based on these two, the system can then rank and recommend a representation. And the language that we invented is called representation systems theory. And its novelty is that it can describe and analyze any formal and informal representation. And it's basically based on the encoding of the structure of a representation. So here's an example of the structure that we want to capture for the Bayesian representation. And here is for the area representation. And the language, and here's a snippet of our language. So the language is very general and it's applicable to any representation. And we encoded not just for these two representations, but we have kind of like a library of representations that we encoded in this, like dot diagrams that I showed you earlier, or logic, or Euler diagrams, and so on. So we encoded the whole library of these representations using this structure representation systems theory. And then we built an algorithm which we call structure transfer that can analyze the candidate representation and assess if it's able to represent all the concepts that I need to have in order to solve a problem. So it basically executes an analogy, which is a transformation from one representation to another. So like here, we're going from base to area representation. And it does so by exploiting the structural similarities between the representation. So analogous structure. So you can see here that it's spotted that there is an analogous structure between the two representations. So this one is just the candidate one, and we will see whether we can transfer from the base to the area. And we have a bit more information here about D and the value of it. And so now the structure transfer can automatically transfer and instantiate this area representation, and so on. It continues doing so until we're done. If you can't, then all the information can't be encoded in this other representation. But if it and that's fine too, because sometimes it's useful even if you don't have a perfect or complete translation from one representation to another, because it might still give you an intuition. And okay, so yeah, so that's the structure transfer. It basically instantiates, so it does this automatic transfer from one to another, from completely formal to informal, from informal to formal, any representation, because it has this, it's looking at the structure graph theoretic kind of approach to analyzing the structure of representation. So you might also wonder now, so this is informational suitability of a representation. But you might want to wonder, what about the user? Because I haven't said anything about that yet. So we work with cognitive scientists to identify a suite of cognitive properties, and these are mostly coming from the literature, from cognitive literature, that representations may have, so that our algorithm can then quantify and qualify the cognitive cost that a particular representation places on different types of users. So for example, the bigger the branching factor that is required in order to solve the problem, the higher the load on the working memory. So, or the more complex the expression, the higher the cognitive cost that is placed on someone with poor problem-solving heuristics, and you know, these cognitive costs have implications for what the system may recommend to a particular user. And at the moment, we are devising various profiling tests and other mechanisms that are going to gauge the level of expertise of a particular user, which should then be reflected in this cognitive cost. And we want to apply this framework in education, and in educational setting, and in personalized tutors. But we believe that this is applicable in any other domain and where humans are interacting with AI or other systems. So one of the things that we're also looking at is that one bottleneck is obviously a library of representations, right? So we're looking at how to use large language models and the repositories of all of the different representations in order to encode them then in our representation systems theory and have a huge library of representations that then we can just analyze. Okay?
So it's not completely clear to me what your tools do concretely. So I have a problem. I have a artificial intelligence with me, and I asked artificial intelligence to show the problem to represent. So it's not completely clear what concretely what is happening here.
So what's happening here is that if a system is a problem-solving system, it needs to be able to choose the representation within which it will present to you the problem and its solution, right? So that you will
in a way
understand
that I can understand.
Yes, yes.
So how the machine know me?
It won't initially unless you specify, like, so this is what we're looking at now. So at the moment we have coded cases from cognitive literature about experts, about novices, and about me. So actually we have 3 levels of expertise. And that's, we can actually even now change the level of expertise, and the representation will then be computed dynamically what the cognitive cost is. But how will the system know your level of expertise? For that, we are doing profiling tests, but I don't like profiling tests because who wants to fill in a profiling test thing? What we are looking into is that your interaction with the system, so in the beginning, it will know nothing about you, but then as you interact with the system more and more, it will learn from your mistakes and things like that, but that's future work really, so. But in principle,
It corrects itself.
yes, yeah, but in principle, the system can already respond in terms of recommendations based on the level of expertise. But obviously, we are now just choosing what the level of expertise is. If you don't know anything about the user. Yeah. Okay. Okay, great. So, making AI machines adapt to their human users in the way that they interact with us and in the way that they present information to us will, I'm posing that this will make them more amenable to humans and ultimately, therefore, more trustworthy. And this is my second message, my second take-home message today.
I want to say you that you already lost the bet because it's already 45 minutes and you are at the last and the half of your presentation.
That's
so
right, yes.
there was no hope that you can win.
With
no
our
hope.
assistance.
You successfully managed to
Exactly.
sabotage. I don't mind at all because you gave me a huge slot. So. All right. Okay, so.
Your second take-out message?
So my second
What was the
take-home
first one?
message is that we can make systems, AI systems, adapt to human users and the problem that is being solved. And I think that will make adaptable AI systems will make us trust them more. Okay, so one of the most powerful technologies that is used in AI today is machine learning. And it's the main driving force behind the proliferation and success of AI systems. And deep learning methods are deployed everywhere. You've got speech recognition and natural language understanding, like in Home Assistants and ChatGPT. And they learn about your tastes and recommend groceries for you to buy and films to watch. And they even help you find your partner. No, I didn't meet my husband online because the online dating platforms didn't exist at that time, but some of you might have. Okay, so the challenge with these AI systems and AI methods is that they suffer from what is known as the black box problem. The algorithms that they use to arrive at the solution or the recommendation are so highly nonlinear and complex that they obscure our understanding of why they came up with that prediction or a decision. And as we are increasingly deploying AI to make decisions about humans, about us, like in law, to compute the sentence for a person that was found guilty, or like in medicine, to help doctors diagnose patients, it's crucial that we address this challenge of explainability, and so that we can explain to the judge why the AI system recommended a particular sentence, and so that we can explain to the doctor why it suggested a particular diagnosis. And this explainability is the third aspect of AI that I think that needs to be addressed in order to make AI machines more trustworthy. So here are two types of examples of a black box challenge and the lack of explanations. So first, an AI system here takes an X-ray of a patient and predicts the grade of arthritis, but with no explanation about what led it to this prediction. So for ethical and legal reasons, especially in Europe, I'm not sure how it is in the States, but doctors have to discover the reasons themselves to see if they agree with the prediction that the machine made, okay? And in this example, the system mispredicts that a muffin is a chihuahua and a chihuahua is a muffin, and in fact, it does so with 95% confidence. And so the lack of explainability, so it doesn't give anything else apart from that. And the lack of explainability makes it really hard for an AI engineer to fix the system and may therefore cause the lack of trust in AI. But there is a new and really promising approach to address this challenge of explainability of deep learning, that a number of people are working on it, and including my group. And it's called concept-based learning. So the essence is that it builds models and therefore predictions based on high-level human interpretable concepts. So here in this example, it can predict that the first image is a hot dog because, I don't know if this is going to show, no, because it's a screen, because it has a bun, it has ketchup, but it doesn't have fur and legs, okay? But in this second image, it predicts that this is not a hot dog, and it's because it's got legs and fur, but it doesn't have a bun or ketchup. Okay?
If the question is, it is a hot dog or not, it's not a question what it is.
No, it's not a question what it is. It is a question of whether it's a hot dog or not. Yes. Okay? So these concept learning architectures are based on a simple idea of a two-step process. So you start with all the low-level features, like, for example, pixels in these two images, right? And encode them in the function G, in the concept encoder, into a set of important concepts that are present in your data, like legs or bun or stuff like that in the image. And then use in the second step in the function F, which is known as the label predictor, it uses all these concepts to make a prediction using them, not pixels, in order to make a prediction of whether the image is, in this case, a hot dog or not a hot dog. And so here X are input features. The function G is a concept encoder, and the C hat are all the concepts that are present in your data, and function F is a label predictor, and then Y hat is your final prediction.
I have a problem here, because if the question is it is a hot dog or not, the concept bone and ketchup are relevant.
Yes.
The concept legs and fur not relevant. So they are relevant for the particular non-dog example that you consider, but you can consider also other non-dog examples
Absolutely.
for which legs and fur are not relevant. So how did you choose these four?
So
only two are justified by the question of dog. The other two are not
it
justified.
depends what's in your data. So if you have in your data, you train the model with data that might contain not hot dogs, and then you will have other concepts present there too, right?
So you have a bank of concepts.
So originally, when this was invented in 2020 by these people, this is not what we've invented. This was the original contribution. You absolutely needed to label all your data that you want to make predictions about with concepts. And of course, that's a massive bottleneck, right? But at least it was shown that it's possible to make predictions in terms of these high-level concepts, which before it was literally a black box, in and out, that's it, nothing else in the middle.
Under the condition to input the concept.
So this image needed to be labeled with various concepts, right? Also, it was completely fixed how many concepts it's called the bottleneck, could take. And sometimes you might want to have more concepts that might not be there in the data, for example, and you want to dynamically change the size of the bottleneck of how many concepts you're using in order to make predictions and describe the output. Yeah.
When it was proposed, was it claiming that it would work as well as the black box, or was it clear that it would not necessarily work as well as the black box?
So at the time, that's a very good question, because at the time when it was proposed, it was thought that, and in fact, it was true for this particular case, that the explainability did come at the cost of accuracy. You did sacrifice some accuracy in order to gain explainability. However, in 2023, we showed that you do not have to do that you do not have to sacrifice accuracy for explainability. And I'm going to tell you more about that in a second. So we build concept learning architectures where you don't need to know about all of the concepts from the outset. The model can discover them by itself and use them in the prediction. So it can use the ones that the data came labeled with and the ones that it discovered by itself. Yes.
Is the concept encoder trained independently from the label predictor? Or
Yes.
Okay.
Yes. Yeah.
Yeah, because I was wondering, it seems there could be some mismatch of content between the output of the G function and just the.
Yes, you are very perceptive because there could be some information leakage there, and people and the way that you train the two encoder and decoder, it matters.
Okay.
And in fact, it's an open question that we are also addressing, but that's kind of like really deep machine learning
That's also an old
understanding of-
philosophical question. What is the content of a concept? It's,
Yeah. Okay, so let me show you how we did this, how we build an architecture where you can discover new concepts. So we used concept embeddings and clustering to discover new concepts. So here, the model can discover a new concept of a tail by clustering the embedding space of the concept of fur. And it notices that there are two other groups, the one that has fur and the one that, the one that has a tail and the one that does not have a tail. And so, so now our system can add this new concept. Obviously, it doesn't say it has a tail. It will say, check out what that means. But that's what it essentially does. And so now our system can add this to automatically discover concepts of a tail and add them to the set of existing concepts and use it to recompute the prediction. Okay, and you will notice that this is really cool now because not only that you can add, you can discover new concepts, but also you were able to actually correct something. So the expert, the main expert can actually interact with the system. And so I'm going to say a little bit more about this.
So, but sorry, you start from a labeling that you already have, or you start from scratch?
You can actually, we're now working on where you can start from scratch, where you have no concepts attached to your data. But you need to get them from somewhere. So what we're, at the moment, we're doing a project where we are basically, if you know the domain of your data, like, I don't know, images of animals, then you want to get all the concepts from the, we are actually going to use large language models to get the concepts from the internet, basically, from the domain knowledge that is
Okay, so you have a bank of images and a certain literature, so bank of concepts in such a way, so you put them together.
Yes. So then you know that you have them. You don't have your data labeled with it, but you know that you can use them. And then, so that you remove this need of having the data labeled. Okay. So, but the main point here is that, remember how I said you can go back and correct? So these architectures that we build now are allowing us to keep the human expert in the loop and enabling them to correct the concepts, right? So here is an example of a cute image that deep learning models have a problem with. So it mispredicts that this is a hot dog. And the concepts that it gives us that it's a hot dog as an explanation for its misprediction contain the information that the model did not spot legs, right? So it said that this is...
I hope that you do not address your dog like that.
Okay. No, we don't dress up. You are actually for Christmas, maybe. Not but no, stop.
We don't want to know.
Yeah. And so now, now a human dog expert or a hot dog expert can come along and say, hold on a minute, there's an error here, let's fix it. And they will say that this image actually has legs. And now a label predictor can of the model can now compute or recompute the prediction again, which fixes it into deciding that the image is not a hot dog after all. And whilst this might be a cute example, we can deploy these AI machines on real-world examples like the arthritis X-ray that I showed you earlier. So we can say that an X-ray shows arthritis of a particular grade. I think here it's grade 3, moderate, because the AI system detected the following concepts in the image. It found osteophytes, and it found narrow joint space, but it did not find sclerosis or bone spurs. And in my group, we are actually focusing on tabular genomic data, and we're hoping to utilize this to discover biologically relevant and meaningful concepts in cancer medicine.
Is this not offloading the black box problem into the embedder?
Into
The concept
the
encoder.
label predictor.
Yeah.
No, because label predictor will give you the concepts that it used for the prediction, and you understand those concepts. Yes, there are non-linear things that are happening there, but it does the prediction in terms of those high-level human interpretable concepts. Because after all, we want to leverage and we want to capitalize on these high capability of non-linear relationships that neural nets can discover, right?
Sorry, go ahead.
So, but in this case, we enable them to give predictions in terms of concepts that we understand rather than low-level features that we wouldn't understand. Well, so the existing XAI methods, the explainability methods, will be all post hoc, and they're mostly for images, where they will highlight the pixels that they might have used for the prediction, right? Such as like Lime or Shap or something like that, right? Whereas here, you actually make a prediction in terms of those concepts, and you output that as alongside with the actual decision.
So this would imply that somebody, probably a graduate student, would have to go prediction by prediction and verify that the labels were correct.
No, you train the model with the data, that you have ground truth data. You train the model, and then you can deploy the model.
Okay, I see.
Yeah. So you have to have some data to train a model, right? Which has the ground truth. Well, it's not always exactly how, because humans are fallible too, right? We would have X-rays that would be labeled with these concepts.
Yes, but you also said that the concept encoder can also discover new labels.
Yes.
Which were not previously in the data.
New concepts.
How are those verified?
I see what you mean. Yes. Okay, that's a very good point, actually, because, for example, and it's very pertinent, especially because we are working on genomic data, right? So our input are tables. It's not something that you can go and look and say, oh yeah, that's what it means. We have 20,000 genes. And so if my concept predictor says, okay, there is a new concept of this assembly of genes, I have to go to the domain expert and say, do you recognize these? Do they make sense? Is it a known thing in genomics? Or if, in fact, what we are trying to do also is with our labeling approach that we are using large language models to go through all of the medical literature, for example, in this domain. In other domains, they'll be just generally whatever large language models being trained on. But in this domain, it would be going through the medical literature to see whether those subsets of genes that were highlighted as a particular concept, as a genomic marker, for example, are already known in the literature, or they're new. And if they're new, that's really exciting, because then we can design, and that's what we're planning to do, clinical trials surrounded through these new concepts to see whether they're biologically meaningful. And that's the exciting bit, really, with this kind of technology.
If this question is getting too into the weeds, let me know. We can talk later.
Okay.
But have you, in this concept encoder, do you use geometric priors at all? Or let's say that you know that a particular thing has a certain number of causal factors and you have an autoencoder with a choke point has that number of nodes.
Yeah, I think I understand your question. So whether we're using some kind of structural causality and stuff like that, this is not really an answer question in the area, right? Like people are now using causal reasoning, and in fact, one of the projects that we are starting, that one of my PhD students is working on, he's trying to do exactly that, to get graphs or causal graphs in order to bias actually he's trying to build tabular foundation models. But yes, so we didn't use anything like that. We just used off the table, off the shelf MLPs, I think. Actually, we tested on several, but it doesn't make much difference. Okay, yes, so yeah, we're hoping to discover meaningful concepts in cancer medicine. More questions, go.
Yeah, this is so cool. When you
We are very excited.
maybe this is too vague a question, but when you've applied this in the past and have been discovering new concepts, like approximately what percentage of the time are the new concepts stuff that people understand versus some kind of incomprehensible computer embedding?
I don't know, I guess. I mean, this is like, it's very recent work, right? So we used it in things that we could verify and validate, right? So we used it on images mostly because we can validate.
But so for images then, is it like 90% of the concepts is like, yeah, that's
Are
definitely
they
legs.
meaningful or not?
Yeah.
Yeah, there. Yes, most of them are meaningful. Yes.
But there's some percentage that I have no idea what the computer is seeing here. Okay.
Yes. And in fact, we are trying to understand how does this happen, and often it's information leakage or other more.
Or it's like a context, something silly.
Yes.
Yeah. Okay.
Is that still a black box, would you say, how it generates new concepts or discovers new concepts? Or is that well understood how that happens?
No, it's well understood, yeah, because we make it. Like I said, in the original methodology that we didn't invent, data had to come labeled with the concept. So then it aligned them squished them into this bottleneck and then made predictions in terms of those. But yeah, so the concepts were completely controlled. Yeah.
So sometimes I discover a solution of a problem, but then I look at it and I say, okay, I cannot explain this to my students. So in a way, it's a black box.
Mm-hmm.
But then the fact that I already found the solution is helping me to find an explanation that my students are going to be able to understand.
Yes, exactly.
Is this something that
It
could
can be used exactly for that reason, yes, as well. We haven't we were very motivated from the medical domain, right? Because that's where we need, because there are collaborators, but also because that's where they need the explanations the most. But we are looking into, because you could use it in the educational kind of setting, because it provides you explanations for the problems, right? Yeah.
Question, is it equally problematic when it comes to trying to fool these systems with adversarial examples, or is this technology going to help us?
It's going to help with the adversarial scenarios for sure. So another project, another application of this that we are going to be using now is I have a new PhD student who she's very interested in looking at the bias in the data and in the models. And using this explainability should be able, we're going to try to use this in order to guard against the adversarial attacks and add explainability to avoid data and model bias. Yeah. Because this is actually very new, it hasn't been really applied to very many areas, right? Like literally, we published this last year, and we are publishing more this year. So it's really very new. Okay, more questions before I move on? Okay, then to conclude this part, my third take-home message is that if we can make AI machines explainable, then they will definitely become more trustworthy. So far, I talked about how we can make AI machines think, adapt, and explain things to us in more human-like ways. But we humans possess a huge amount of domain knowledge that we discovered or developed over millennia. So we are doctors with our insights about correlated symptoms. We are mathematicians with our insights into complex problems and machines can't really solve. So for example, Euclid proved 2000 years ago the theorem about the infinite number of primes. No reasoning machine has been able to solve this, to prove this theorem. And
there is no proof by machine of the infinity prime number?
Discovery.
Not discovery, they never discover it. They can't redo the proof.
Well, you can redo the proof nowadays, but you can't deploy it and the machine would be able to just prove it. You have to give it a proof. Yeah. So, so mathematicians have recorded their discoveries over centuries in books, journals, MathWiki, Math blogs, Stack Exchange, and in comparison, the proportion of maths that is formalized for machine reasoning to say, let's say in Lean or in Isabelle or in Koch or in Mizar, is tiny. And similar is true for other areas too. So for example, the domain knowledge in medicine or biology or other fields is in journals and ontologies and knowledge graphs. So the size of this informal human domain knowledge is vast. And I am proposing that we need to capitalize on this wealth of human formal and informal knowledge in order to make AI systems capable of such human level reasoning and lead us to trustworthy AI. And large language models such as GPT-4 nowadays really enable us to access this vast resource of digitized human knowledge and put it in the format now that reasoning machines can take advantage of and use. So by integrating human informal knowledge, we can enhance the problem-solving capabilities and the human-like nature of AI solutions. So in my group, we decided to do just that. So let me give you an example. So here is a problem that machines are not very good at solving. And in this case, it's because they may not know anything about the lemma about the greatest common divisor or the least common multiplier. And but mathematicians have recorded this solution, for example, on Stack Exchange. And we built an architecture where we employ large language models to harvest these human informal solutions. And in fact, in this case, ChatGPT has found this human solution to our problem that was somewhere recorded in something, in some repository. Okay, so, and the first step in this process is to process this human proof into an informal proof, what we call proof draft. And we can use either human-supplied informal solutions, so like we actually had a whole bunch of mathematicians writing solutions, we could do that, and then we use them. Or we can also use large language models to generate new informal proof drafts from human proof corpus, like on Stack Exchange. Right? Okay, we then ask a large language model to auto-formalize them into what we call formal proof sketches. And so here is this proof sketch. And these proof sketches basically encapsulate like a high-level idea of the proof that came from the informal human proof. Okay? And then we copy segments of these drafts, so natural language, as inline comments in this formal sketches to create a good alignment between a formal and an informal proof. But then you will notice that there are still gaps left in the proof. And we use a formal theorem prover to close those gaps. And in this case, we used our in-house theorem prover called Isabel. And so we pass these sketches to the machine reasoner, which will check that the steps are correct and solve any of the gaps that remain in the proof sketches. And we call this step proof. So here's the high-level sort of overview of the architecture for the entire process. So you can call it draft, sketch, and proof. So draft first, we use humans or large language models, and in our case, it might be Codex or Minerva, these are the language models, to draft these informal proofs. Now, we sketch to transform informal drafts into formal sketches. And we used, again, a large language model Codex for this auto-formalization. And notice how we use large language model for two purposes here. The first one was to harvest informal human proofs. And the second one here, a different purpose, was to auto-formalize these drafts into sketches. We could use any other, in fact, in later experiments, we used a different language models to do that. And finally, we have proof. So we can use an off-the-shelf reasoner. Here we used Isabel to verify the steps and close the gaps in the proof sketch. So we have draft, which is human knowledge. We have sketch, which is neural methods. And then we have proof, which is symbolic methods. So it turns out that this approach vastly improves the reasoner's power, and it also produces proofs that are much more aligned with the human solutions. So now we can prove Math Olympiads problems that we can solve them by this approach, which before was not possible. And remember the theorem about the infinite number of primes and how machines could not prove it. Now, and the Euclid came up with it like 2,000 years ago. Now we can actually use draft, sketch, and proof approach to take advantage of Euclid's proof. And it turns out that now a machine would be able to prove it, whereas before no machine. And there's additional sweetener here. Yes.
So just to be clear,
yeah,
you're training the auto formatter not to prove the thing, but to create output that is compatible with the theorem prover.
Yes, yes. We are basically saying, here is my human solution, right? And you can get it either from a human or you get it from a large language model from Stack Exchange, let's say, right? This is the human solution. So now transform it into this sketch that is in the language of, or it's going in the direction of the language of your theorem prover. Then you use another language model. Well, we use the language model to then transform that sketch into Isabel or Lean. We did it for both. And then you deploy Lean or Isabel to check the steps and fill in the gaps.
I see. So to make a probably big oversimplification, you're training this auto formatter to basically create a homework assignment for a competent student where it has the steps of the proof and clear, like there's a clear way in between.
I guess you could say that, yes, because you are reducing the search space for the theorem prover, but there's a lot more going on here because you are going from natural language to formal language. But yes, it's in principle, I guess, yes.
In a very simplified way.
Yes, yes.
I see. Thank you.
Can I ask, what would be the prospects of, it has not been done yet, to incorporate like a non-procedural program like Prolog into this kind of thing? And to teach it, definition of GCD and etc. And then it is going, or she is going to proves automatically many properties about the numbers, etc. If you teach
If you give it all the
definition,
background theories.
not I mean a
yes.
logical definition.
Yeah.
Is
Yeah,
something have been done yet?
you can use that in terms of, in fact, we have used this in terms of which conjectures, well, actually, we're looking at conjectures. Which conjectures can you come up with that would help in the theorem proving solution? But you're actually saying which theorems and lemmas can you find that you add to your, yes.
Automatically.
Yes.
He has been able to find.
You could, and the fact that it's prologue or not is neither here nor there. It could be any language.
Mhm,
Actually.
yeah,
So,
But it's no procedure. Prologue, it don't give you the definition, it find for you.
So how confident can we be that proof produced in this way is actually the proof of the theorem that
Very
we
good
want?
question. Very good question. You're saying who's decided that actually this translation into the formal thing is actually the thing that yes.
At some point, it
So what we-
translated into something very easy
Yes,
to prove, and
yes.
then the prover came out with a proof.
Yeah, very good. So we did this. We actually created and checked with the human expert mathematicians. We spot checked like 200 of these theorems and checked the accuracy, and in fact graded the errors that were being made from catastrophic, where it completely misunderstood everything or hallucinated everything, to like minor, just because the syntax was wrong or something. Yeah, we did, and it was how accurate it was. So this is very new work that is coming out in December. It is, if I remember correctly, it's just plain doing it like that was vanilla approach was about 75% accurate. Yeah.
So, I see.
Well, if it's on the shelf, like it's not bad, right? Either nothing or.
Yes.
What is so difficult about Euclid proof? After all, it is a schematic proof.
Great.
Why is it so difficult?
I don't know.
Because
I would have to look into
the schematic proof, and then you have two options, either is prime or is not prime, but this, so this is not decitable point.
I would need to have a look into
Step
it.
it was not decitable.
Mathematicians here might know better.
Maybe it's a combination of addition and multiplication and order. So it makes.
It's a proof by contradiction, right?
No, it's not a proof by contradiction. It's presented as a proof by contradiction, but in fact, it's not essentially it's not a proof.
But think about all the concepts you have to put in. You have to put in the Peano axioms, and then you have to put in the primality condition. And
No, you don't need so the proof is very
It's a-
simple.
it's a
Do you
second
not
order
need primality?
Ring's fine, but
Yeah.
I don't know.
It's not by
So the fact that
so,
it is that
because what you prove
is
is
larger
that
than
for
any
any
others, and therefore
natural prime, there is another that is
finite
greater.
domain.
So you do not need to contradict the fact that n is the greatest. Take n and I construct one that is greater. I don't construct. I prove that exists one that is greatest exists. And in which way? I construct one, and then I tell either it is prime, so I have constructed, or there is a prime that is greater than the other, that is a divisor of this one. So I have in any
But
case
if
one
you-
thing that is
But
prime.
you suppose that there's no one, then it gets.
Sorry?
If suppose that there's no,
There is no,
okay, no
prime.
Yeah.
No. You have to support that there are.
Yeah.
The proof support there are at least one prime.
Yeah.
Otherwise it doesn't.
That's not a point here.
Okay. All right. Homework. So I wanted to say that there's an additional sweetener in this approach, because now these solutions are actually formally guaranteed to be correct. And this process basically has a potential to easily formalize and verify the work that human mathematicians have done, because now we can be translating it and auto-formalizing and using this draft, sketch, and proof approach to check whether those proofs have been correct or not. Interestingly, in this process, it does not even matter if the human solution was incorrect or not, because we used it, or the pipeline or the approach used it in order to constrain the search space, because it gave it a frame, and then it would check anyway whether it's correct or not. And in fact, even fix various steps. But my point here is that now we could use this to actually check all of the type of work that mathematicians are doing, and to have such a formal guarantee that the solution that the system is coming, the system is coming up with is correct. It will definitely kind of increase our trust in these machines, right? If we have correctness guarantees. So we can deploy them then, especially when you're doing formal reasoning in scenarios where correctness is key, like safety critical applications. So we showed that the benefit that AI machines could reap by capitalizing on the human domain knowledge. And we have the technology today that we can do just that. And so whilst we demonstrated this in maths, we believe that the general approach can be utilized in any area. And the large language models are opening the doors to that. So perhaps, you know, in the future, we'll be able to collect enough grains of human knowledge and this technology to enable machines to discover new solutions to existing open problems. So as my fourth take-home message, I showed you a way to capitalize on human knowledge. And this makes machines more capable and also more human-like. And it turns out, well, I think that therefore it leads to more trustworthy AI. So in conclusion, building...
Finally!
Building AI machines that we can trust requires a multifaceted approach. And through our research, I have focused on 4 key aspects: intuition, adaptability, explanations, and leveraging existing human knowledge. And together, these advancements will play a crucial role in enhancing the trustworthiness of AI machines. However, trust in AI goes beyond technological advances alone, and we must address other ethical factors, other critical factors such as privacy, regulation, and ethics. And personally, I'm deeply involved in the ethics of AI design and deployment, and I work alongside institutions such as the Center for the Future of Intelligence in Cambridge, and I also collaborate with the UK government to tackle the ethical concerns head-on. And the need to get everybody involved, us with technical expertise, and everyone in this room, experts in areas like ethics, philosophers should have things to say about ethics, is urgent. And people are worried. But despite the contrasting narratives surrounding AI, ranging from doomsday scenarios to potential cures for diseases, I firmly believe that the future lies in the hands of human experts supported by intelligent machines. And trustworthy AI machines will empower us to make more informed decisions, to revolutionize our industries, and to address the complex problems or global challenges that we are facing. By imbuing these machines with insight, adaptability, explanations, and knowledge, we foster trust and we unlock the boundless potential to serve the greater good. And in this partnership between human intuition and ethics and AI and reasoning, we have an unprecedented opportunity to solve some of the world's most pressing issues. So together, let us embrace this potential and shape a positive future. Thank you.
Thank you, the chair. You presented, so you are the chair.
And then we have
question if-
2 hours of discussion without the chair. I don't think I'm needed.
Yeah, just wanted to thank you for the good presentation. Wanted to ask you what's your opinion on just publishing the models, at least the architecture, talking about explainability, and the last step, what was the last step? The human
Knowledge, yeah.
right. So let's just say people publish their models, publish their training data, publish their weights, the model that would be perfectly explainable and not
Yeah.
let any bias creep in, right?
Yes, yes. So, I mean, if you deploy this kind of architecture, yes, but so you are probably,
Reproducibility is the main thing, right?
yes,
So
we
if
are very
do-
hot on reproducibility.
Yeah.
So academics are very good. Like if you go to publish at NeurIPS, biggest conference in machine learning, you have a checklist that all your code is there and is reproducible. It's put in the repository. Anybody can use it. You have to be able to reproduce. So somebody has to be able to just take it and reproduce it. Then the same results that you got. But I think what you're referring to is the fact that OpenAI and these large language models, they don't publish any of this, right? But they're, so there's a
Facebook does, so
proprietary.
this was
Yes, so for example,
Asking
there are
opinion.
loads of other now competitors, I guess,
Mhm.
large models that are open weights models so that people can take them and then tune them and actually do something with them rather than just deploy them, black box type thing, yes. So Mistral is, I have to say, I'm very proud. Today, my PhD student who was doing this work on draft sketch and proof has passed his Viva with no corrections. And he works for Mistral now, where we are all very hot about open models. And so they publish the weights. We used, in a lot of our experiments, we used Llama, for example, because it's open model as well. So, yeah.
Thanks.
Oh, I wanted to say thank you to these people, but I've introduced them before. And if you were asking to get in touch, yes. We always collaborate a lot, so very welcome. Yes.
I'm curious, why do you think there is a worry about doomsday concerns? Where is that coming from? And what for supposed such as
It goes back to what, Terminator or something?
Oh,
Yeah.
much earlier.
Much earlier.
Robots use universal robots.
Yeah, taking over the world. I think it's a lot of it is media misinformation. People don't understand how it works. I think that it has changed now. Like, it's a little bit cultural. Like we are concerned. Actually, even we are not very much concerned now anymore whether we're using AI or not, because we don't even know we're using AI. But you have your watch, you have this, that, and the other. We're just using it. In Asia, like in China, for example, they're completely blasé about sharing data, whatever. They don't see a problem, especially the younger generation at all. So they have a very different attitude towards that. And I don't.
their personal information?
Yeah, they share information very easily.
Oh.
Maybe they were brought up in a system like that to think of it that way, but I don't know. Anyway, that's not the point. The point is, it's unhelpful. It's very unhelpful because it is the future. It's not going to go away, right? And we will be a success, or our work will be a success when nobody will notice it anymore, right? It will be very, boring, pedestrian, because the solutions are so integrated into our lives that we don't notice them anymore.
Yeah, in Japanese culture, it's precisely the opposite. They see robots as friendly. There are many in anime. They appear
That's
everywhere. They are the savior of the day.
Yeah.
They're viewed as good thing.
Yeah, and the stuff that we do, we're never working with the motivation to replace humans. We are working with the motivation to help humans or to involve humans in the decision making, because I think this complementarity of what we can do with machines and what humans are better at will be the key to success in the future. So I do understand that other people might adversarially deploy the technology, but that's for politicians and possibly even philosophers to sort out with, regulation and various other protective measures. Yeah. Yes.
Yes. So I'm wondering why you choose the title trustworthy, because in fact it seems to me that what you explained to us is not whether or how we can make AI trustworthy, but more how can we make it easy to use, adapt to us, appropriate for other, so friendly in some sense. So when you use trustworthy, you seem to imply that the trust depends on the degree of being friendly. So this is what you think, that something is more trustable for us as more is appear as
Yes, I take your point. I think that yes, if that's one aspect, is the intuitiveness and adaptability. If a system is producing solutions that I understand, and if the system is adapting to me, then it's in human nature to trust and rely on it more. But the main factor for me personally is actually the last one. Well, the last two, which are explainability. So I get the explanations, the reasons for the decision, so I can trust it, and verifiability, so that I get the correct solutions in the end, and I can trust it, therefore.
But the trust here is psychological. So what does it mean that
I would say possibly the first two you could potentially classify as the psychological factors, and I think that the last two, I would say that they are technical and sort of
okay.
Technical.
And that's another question. So if I understand well, the end of the story is that whatever it may be, trustworthy of AI is what is trustable is not AI, but is a property of the AI and the way if I use it.
Yes.
So
yes.
the good question is not whether AI is trustable. The good question is where AI used in a certain way by a certain audience is trustable.
Yes, and you will notice that my title is not, is AI trustworthy? I say, how can we make AI trustworthy? So making is the big thing, because I built.
So the real problem is how do we use it in such a way to make it trustworthy?
Not necessarily, no, because I think that the machines are lacking properties that would make us trust them. So if they are not verifiable, like for example, ChatGPT, right? It hallucinates stuff. So one of our projects for the future that we're now setting up is how we can do this neurosymbolic reasoning, where we can bring in verifiability of the fourth of my approaches, so that we get some correctness guarantees from these models. Because at the moment, they are like, we use them, but our students use them and they write these essays or whatever, but they don't check that. I mean, the ChatGPT can be really good at, sounding very authoritative and very genuine and everything, even giving you a reference that is completely bogus, right? And so you need to check whether everything that you get out of a large language, ChatGPT. So what I'm looking into is that, and you can't trust it, right? What I'm looking into is how we can provide some correctness guarantees with systems like that, using these symbolic approaches and adding to them.
I understand that this is something that we can do.
Yeah, really good.
But there is another approach that could be possible. I can take ChatGPT as it is, ask a question, and then not address directly the question, and so to ask other questions, so to cross questions in such a way to use it as it is in a way that is more trustful, depending on the way in which I use it. So instead of asking one question,
You
I
still
ask
don't have.
27
Yes,
questions that
yes.
are crossed one
And
to
you
the other.
still will
and
not
I-
have the guarantee that it could be. correct.
Of course, but I think that the question is a question
Yeah.
of guarantee. You will
Okay.
never have the guarantee of nothing. We are philosophers, so
Yeah.
no guarantee
Okay,
of nothing.
I
But you can increase the degree of,
Okay,
if you use in an appropriate way.
Yeah, okay, I think I understand your point, which is that there are different ways of approaching trustworthiness, and one way is, well, I'm focusing mostly on how I can build systems that are more trustworthy, whereas you are questioning of whether we can use existing systems in a way that will give us more confidence that it's doing the right thing.
Exactly. Existing system also improve the system, because also when the system will be improved very fantastically, but you still, it cannot be considered to be absolutely trustworthy.
Yes.
So even with your improved system, I need to know how to use it in order to increase my degree of trust.
Yes.
Can I turn your question an engineering question? So to make, say, language models more trustworthy, do you see like the way forward in changing the language models or embedding the language model as they are, like referring back to what Marco said, in a bigger system that is doing the verification outside of the language model?
You mean like post hoc sort of thing?
I mean, like in your example with the math proofs, right? The verification was not done by the language model, but by Isabel, right? But I know also that a lot of people are thinking that they can solve the problem, say, with language models hallucinating by kind of doing some kind of surgery in the models, right? So there are activation patches, there's mechanistic interpretability, all kinds of approaches to that. And I was just like wondering what your opinion is, which of the two approaches is more promising?
I can't answer that because we don't have the answer to that.
There's a LLM studio that would give it enough GPU, you can load multiple LLM models and actually make it figure out. We cannot let them fight it out. At least compare the outputs.
Yeah, but that would not necessarily increase trustworthiness, right?
No, but at least get you the bias or the outlier.
A question on the chat.
I think we're going to try to do it both ways.
Okay, yeah.
So
It's an engineering problem in the end, right?
Yes, yeah, it will be. Yes, like you can't do any, we will be using probably, I don't know yet, Mistral or Llama. The open rates, yes.
So another question about the concept bottleneck model. So if I see a red splotch on something and it looks like it's on a hot dog, I'm going to think it's ketchup. But if I see a red splotch on my tile floor, I might think it's blood, right? So there's a sense in which the prediction of the concepts relies on a prediction of what the big end thing is, right? So presumably that is what your AI is doing, right? And then isn't there some sense in which the black box is sneaking back in because there is a model of whether or not this is a dog, which is going into the prediction of whether it's blood or whether it's ketchup?
I wouldn't say that that's creeping in back with the black box because you have data, you're learning from it, you can correct it and you can fine tune it and you can introduce more diversity with more different scenarios and therefore your model will become more reliable to be correct, even with these unusual cases. In fact, we are mostly interested in the unusual cases, which is difficult because most of the data will not have them, right? Especially for medicine. So I don't see why that would be reintroducing the black box, really.
Well, except insofar as, okay, why do you think that this red splotch is ketchup and why do you think that this red splotch is blood, right?
It's a probabilistic approach, right? So it will always start with something, but then you need to take the whole context into consideration, right? So, and it will give you a probabilistic answer in terms of confidence, right?
I follow up to my question. I don't think I put my question very well on concepts. how are you understanding a concept? How does the machine understand a concept? Is it
The machine doesn't
and-
understand.
well,
the concept.
It's a circle and it's a sphere in an embedding space, right? If I understood correctly.
I mean, you're talking philosophically, right?
Well, okay, so here's one way to define a space of concepts relative to a set. There's a complete bijection between the possible concepts and the
And you
power
can call
set
them
of the
something
set.
completely different. Yeah, yeah, absolutely.
Is this like how this is what concepts are?
You can't get away from that.
Okay.
You're gonna have to have some human here to say, these are the concepts for this domain, right?
So it could maybe
But you
expand.
might call them something like in a totally different language that doesn't mean anything to you, right? You can't get away from that.
So with images, are the sets like pixels? The set of pixels?
So in images, it's not the set of pixels. It is basically saying in this image, we have these concepts and yeah, that's it. No, nothing more than that.
Okay.
So
So like a tail, it's how does
it's
it?
an embedding space. So
I'll have to. This is I'm sure from ignorance. I'll look up embedding spaces.
Okay.
Yeah, thank you.
So sometimes having assigning trust to a person or an explanation that the person is giving us, it's not only about having or not an explanation, but relying that the explanation is really justifying the facts. So, for example, if I have a person that tells me, yes, I know that you cannot sleep, but this is because your neighbor put a crystal that is emanating bad energy, and this is not making. So, okay, you are giving me an explanation, and I see that your explanation is very complete. But I cannot trust that explanation because there is no reality behind it. So.
yeah, so you are saying that you're basically it's a related question. Where do these concepts come from, and are they related to the input that you are putting in? I really think that there is no way of getting away from that. You have to have a human input somewhere in where it says this is the ground truth, right? It's the same as if I'm translating some maths into some formalization. Am I really, am I really, doing that step?
Yeah, that's this formalization corresponds to the problem.
Yeah, exactly. And here you know how the architecture works, so you know that there is nothing else in the process that could sabotage the causality, I guess.
Our system is open to anyone to use
Yes.
it.
Yes. Yeah.
Is it friendly like in ChatGPT or for?
No. These are the models, right? These are the architectures you have to then. You can either take them as trained models, so you can just use them. You need to. I mean, we didn't do the APIs and all of that to make it beautiful. But if you are used to working in machine learning with models, then you can. Yes. But hopefully there are instructions on how to do it. That my students have put on GitHub the instructions of how to do all the steps.
Okay.
Yeah.
Oh, I think we are.
Do we have more online? Did you say?
No, I was looking if we had, but no comments on the chat, so I don't think we have questions online. It is almost 6 o'clock, so I think it is time for us to thank our speaker for the wonderful talk. And